So here we are going to learn about a new term called rectangular hyperbola. So this topic is rectangular hyperbola, referred to its asymptotes as the axis of the coordinates. So let us see what we are going to discuss here. So right now I have nothing but a hyperbola whose a is equal to b. So until now we've been seeing x square by a square minus y square by b square equal to 1. But it is possible, right, that your a and b both are the same, right? So your a is equal to b. Such hyperbolas where your a is equal to b, they are called as your rectangular hyperbolas. So what happens when your a is equal to b? The formula for eccentricity is under root a square plus b square by a square, right? If your a is equal to b, then it will be a square plus a square by a square, which is equal to root 2, right? So those hyperbolas whose eccentricity is root 2, they are called as rectangular hyperbola. So this was a simple definition for rectangular hyperbola. So here I have a rectangular hyperbola. If the rectangular hyperbola is like this, then these blue lines are the asymptotes, right? So as I told you, asymptotes, the pair of equation for asymptotes and the hyperbola, they just differ by a constant. So equation for asymptotes is simply x square by a square minus y square by a square is equal to 0, right? So they are differing only by a constant. So that means x square minus y square equal to 0. That means x equal to plus or minus y. So x equal to y is this line, x equal to minus y is this line. That means this angle is 45 degree, right? So I now have the equation of the asymptotes. The next thing that I will do is I will take these axes and I will rotate them by 45 degrees. I will rotate this and this, both of them together. So I'll basically put a screw, hold it from here and rotate it by 45 degrees. When that happens, these axes will now meet your asymptotes, right? So when your axis becomes your asymptotes, then you'll have a new parabola. Which is passing through this, right? Something like this, rather something like this. So let me just extract what just happened here. So in fact, let me use a different color. So these green lines have moved. These green lines have moved up to become maybe this red line, right? Such that the green line is now coinciding with the existing asymptotes, x equal to plus or minus y. So simply what it means is, this is about rotation of axis. Your x axis has been rotated by 45 degrees, so your x axis has become this, right? And your y axis also has been rotated by 45 degrees, so it has become this. Now with these two as the axis, you will have another parabola, and that is this parabola. This parabola will be of the form, this new parabola will be of the form xy is equal to k, right? So from x square by a square minus y square by a square equal to 1, I've come to this hyperbola, which is xy is equal to k. I need to find what k is. So this hyperbola is obviously passing through this point called a by root 2 comma a by root 2. Why? How do I know that this is a by root 2 comma a by root 2? Well, that is because this was your vertex, right? Your vertex was at a comma 0. After the rotation, the distance between the axis and the vertex will not change, right? So the distance was a. The distance between the origin, the origin and the vertex was a. So here also the distance between the origin and the new hyperbola has to be a. And also, so let x comma y be the coordinates, right? Let x comma y be the coordinates. Also, the point is lying on this existing the asymptote, which was x equal to y, right? So your x, y are the coordinates, x equal to y, so x comma x are the coordinates, right? Also the distance is a, so under root x minus 0 whole square plus y minus 0 whole square is equals to a. So 2x square is equals to a square, so x equals to a by root 2. We are not taking the negative one because we're just concerned about this one. So you'll also have a minus a by root 2 comma minus a by root 2. So your parabola will also pass through this. It will pass through this. It will also pass through this. So what I will do is I'll just put a by root 2 here. So a by root 2 into a by root 2 is equal to k. That means your k is a square by 2. So let a square by 2 is equal to c. if you let a square by 2 equal to c, then xy is equal to, in fact, let a by root 2 is equal to c. Let a by root 2 is equal to c. So what you will finally have is xy is equal to c square. That will be your final equation. So this is a very interesting hyperbola. Now you know where this hyperbola is coming from. You first had this hyperbola, you found its asymptotes, then you rotated your original x and y axis such that they coincide with the asymptotes, and now with respect to those asymptotes as the axis, now you have a new parabola whose equation is xy is equal to c square, where your c is equals to a by root 2, right? So this is a new parabola, right? A new hyperbola. Every point on this hyperbola can be written as, in the parametric form, it can be written as at comma a by t. And why is that? In fact, not at comma a by t, it is ct comma c by t, because the equation is xy is equal to c square. So ct, if you put this point in this, ct into c by t will be equal to c square. So parameter will get cancelled and c square will be equal to c square. That means for any value of t, this point will lie on this hyperbola. That's why this is the point in the parametric form. Now there are lots more things that you can find about this parabola. If I ask you to find the equation of the tangent, you will differentiate this curve, find dy by dx, and then substitute x1 y1 and get the equation of the tangent. You can get the equation of the normal. You can also get the equation of the midpoint of the chord whose midpoint is given to you. Like everything that we have seen for normal hyperbolas, you can also find for this, because you already know the methods as to how we did it. So there's no special section that I will dedicate for deriving those for this, because you already know the concept. So you just have to just do the same things. It's all about differentiation, putting the point, or getting that quadratic in which you equate discriminant to 0. Like those methods that we have seen in the previous hyperbolas, all of them can be applied to this. Just that this is a new equation, right? Just a new equation and a new parametric form. Until now we have been saying a secant theta comma b tan theta, and suddenly we are seeing ct comma c by t. So just the parametric form was really new, but everything else you can always derive with the existing concepts that you already know and that you already seen in the previous sections. So with this we conclude the section of rectangular hyperbola. I just had to introduce this to you. It's upon you to go back and study the properties of this rectangular hyperbola, because the properties are all actually coming from, so its properties will be like equation of tangent, equation of normal, and in various forms, like equation of normal in tangent in point form, in parametric form, equation of normal in point form, parametric form, equation of pair of tangents from a point outside, equation of a chord whose middle point is h comma k. Everything that you have seen, all those, if you bring them together for this, it will become, that section will become properties of rectangular hyperbola. So I suggest you to read that on your own. Let's conclude the chapter hyperbola with just one more topic called concyclic points on the hyperbola xy equal to c square. Let us conclude this chapter hyperbola with this final useful result of basically concyclic points on xy equal to c square. The derivation is lengthy, so I'll just give you the result, and result is slightly important. You might just get a random question from this topic, and mostly if you get it as something which is formula based, it will be on this formula, because the derivation of this is slightly lengthy. So I have this hyperbola xy equal to c square. As you see, xy equal to c square looks like this, right? We've already seen that in the previous section. So you have xy equal to c square. Any point on xy equal to c square can be represented as ct comma c by t in the parametric form. If I have a circle which cuts this xy equal to c square in 4 points a, b, c, d, as you can see, this circle is cutting the existing hyperbola xy equal to c square in 4 points. Let the parameters of these 4 points be t1, t2, t3, t4. If the parameters are t1, t2, t3, t4, that means the coordinates are ct1, c by t1, ct2, c by t2, likewise ct3, c by t3, and ct4, c by t4. So you have the parameters t1, t2, t3, t4. If these 4 points are actually lying on the same circle, then this relation has to hold good. t1 into t2 into t3 into t4 has to be equal to 1. Right? It's easy to remember this result. You have a circle cutting this hyperbola in 4 points. If the 4 points are actually concyclic, then the parameters of those 4 points the product of the parameters should be equal to 1, right? This is an important result that I felt that you should remember. With this, let's conclude this chapter, Hyperbola. I shared everything that was important as far as this chapter is concerned, and in fact, it's been a repetition of what we have seen in the previous chapters. Almost everything has been the same. If you change b squared to minus b square, your ellipse becomes a hyperbola. So we've seen that a lot of formulas just have this difference, b square and a minus b square difference, right? That's how similar all these figures, your parabola, ellipse, hyperbola, and circles are. Like, they have so much in common that if you learn one thing properly, you just have to learn a little something, like a little concept that's different in order to get thorough with the next chapter, right? That's how the entire coordinate geometry is. So with this we actually end coordinate geometry. So I hope you found the entire session useful. Let's start with the next section. Thanks for watching this.